Bismillahirrahmanirrahim. This is lecture number 17. In this lecture we will discuss some exercise. These are the exercise of chapter number 5 of the book Waves and Rays in Elastic Continuum, Continua. We have first type of exercise. We have in this exercise we have given that we have a continuum whose symmetry group contains x2 x3 plane. So this and due to this x2 x3 plane as reflection, so due to this reflection we have these results, that these are the strain components and these are the stress components. In strain components we have S12 equals to minus S12 dash, S13 equals to minus S13 dash, and these are the stress at T12 equals to minus T12 dash, T13 equals to minus T13 dash, and all the other components of stress and strain, they are remain same. That means T23 will be equal to T32 dash, S23 will be equal to S23 dash. Similarly all other diagonal components. By using this type, these and stress strain equation, you have to show that all these components of stress as elasticity matrix equals to 0. After this we will see that this matrix corresponds to the monoclinic matrix when we are taking x1 axis along the symmetry axis. Now here all the continuum has a symmetry group. See, symmetry group under matrix multiplication, and that symmetry group contains the transformation matrices. For example, that if we are saying that we have monoclinic continuum, and what would be the symmetry group for that monoclinic continuum? We have done the result for monoclinic continuum. Basically we have to use all the matrices given in the symmetry group of the particular continuum, then we have the result of elasticity matrix for that continuum. Let us take that we have monoclinic continuum. In the monoclinic continuum we have, in symmetry group of monoclinic continuum there are 4 elements. What are they? First would be the identity. Then we know that there is center of symmetry. That matrix would be minus 1 0 0 0 minus 1 0 0 0 minus 1. Then its inverse should be there. It is the inverse of itself. Itself inverses. Again, where we have said there is twofold axis of symmetry, and what is that? As we have suppose we are taking x1 axis, then what is the transformation matrix for that axis of symmetry? We have twofold, and we are taking x1, so that would be 1 0 0 0 minus 1 0 and 0 0 minus 1. Now to complete the group, we must have that any product of any two matrix would be there. So when you will multiply the matrix of center of symmetry and this x1 axis matrix, then you will have minus 1 0 0 0 1 0 and 0 0 1. This matrix is correspond to this reflection. So it means that this symmetry group is this is corresponding to the monoclinic continuum. So we to have the result of elasticity matrix, we have to use all these components of symmetry group. But we have seen that there is no effect on the components by using center of symmetry, and we have calculated the result by applying only x1 axis. Transformation matrix corresponding to x1 axis, and you will see that by doing this example you will see that we have that we have no need to apply the fourth component. Result will remain unchanged, that there is no effect, because that is the product of these two components, center of symmetry, transformation matrix for center of symmetry, and transformation matrix for x1 axis, asymmetric axis. The fourth is the identity. Obviously this is due to this we have no effect on components. Let's see that whether we have monoclinic for x1 axis or not by the help of this example. We have this test equation. Calculate T12, calculate T12 dash, C16 we have symmetry, so C16, C26, C36, C46, and dashes on stress or strain. Apply the given information. These are equal, these are S13 equals to minus S13 dash, and this is S12 equals to minus S12 dash. We have this, and we have given this T12 equals to minus T12 dash by putting this value here. We have this T12, no, compare T1 equation 1 and 2, we have these components 0. Again using this type of result, we have T13 equals to minus T13 dash. Calculate write T13 dash, then use the given information, then you will again have T13 with the help of this equation. Compare T13 and T13, you will have two equations like here, equation 1 and equation number 2 for T12. In this you have equations for T13. Compare both equations, you have this type of result. By using this in matrix, in general matrix of C, we have this, and you can see that this is the monoclinic matrix. This is the monoclinic. This is the elasticity matrix for monoclinic continuum when we are taking x1 axis along the axis of symmetry. So you can see that we have the same result. That is why we have used only minus 1 0 0 0 0 1 or 0 0. What we have used is 0 and 1 0 0 0 minus 1 0 minus 1 0 0 0 minus 1 when x1 3 axis is above along the axis of symmetry. So it means that you can have this type of result by using minus 1 0 0 0 1 0 0 0 1. No. At second exercise we are asked to find the stability conditions for hexagonal continuum. Sometimes we use transversely isotropic continuum for instead of hexagonal continuum. They both have same matrix. What is the stability conditions required? Stability conditions require that matrix C should be positive definite. Now this is the matrix C for hexagonal continuum. So with the help of positive definiteness of this matrix C, we will see that there are some restrictions on the components of this matrix C. Let's see what are those. This should be positive, this should be positive, this should be positive, and this should be positive. By putting this should be positive, we have C11 must be greater than C12. This is 1, this is 2, this is 3, and this is 4. These 4 from the positive definiteness of matrix C. Now we can write C in the direct sum of two submatrices. What are they? C1 and C2. By using the block matrices C1 and C2, these are the non-zero block matrices, other two are zero block matrices. Now this is C1 and C2. Now we will see the positive definiteness of these C1 and C2. C2 is straight away positive definite with the help of 3 and 4. Because we know that if you have a symmetric real matrix, then it would be positive definite if all eigenvalues are, if and only if all eigenvalues are positive, or determinant of the leading principal minors are positive. So you can see that is eigenvalues of C2 will be C4, 4 and this diagonal. So to have positive definiteness of C2, all the eigenvalues must be positive. So from 3 and 4 you can see that, from 3 you can see that C4 very positive, and from 4 you can see that C1 1 greater than C12 means that this eigenvalue will be positive. So C2 is positive definite. For positive definiteness of C1 we have this. There are 3 conditions for the positive definiteness of C1. One is C11 positive, determinant of C11, C12, C12, C11, and determinant of matrix itself should be positive. So the first condition is coming from equation number 1, that C11 is positive. C11 is positive. So other 2 conditions are this should be positive and this should be positive. See, this is equation number 5 and this is equation number 6. Now from equation number 5 we have this equation number 7, that we have this type of restrictions on equation number 7. Now you can see that these conditions are coming from the stability conditions of the matrix C, that we are using the stability conditions and getting some constraints on elasticity components of matrix C for hexagonal continuum. Now from 6 we have this, we have rearranged this again, we have rearranging, and we have this type of result. And we know that from equation 4 this is positive, so you can write this inequality as now this is the inequality number 8. Now what can we say from this 8? We know that left side should be positive, greater than 0. Why? Because right is C13 square, so this would be positive, so this would also be positive. So we have C33, C12 plus C12, this product of these 2 factors, C33 and C11 plus C12 should be greater than 0. So when the product is greater than 0, then we have 2 type of condition, that either both components are positive or both components are negative. So we know that C33 can't be negative, this is diagonal component. So if this is positive, then this must be positive, and this is positive, so this must be positive. So this is again one condition. Now we have total these conditions, stability conditions of hexagonal continuum, 1, 2, 3, 4 and 8. From 7 you have C11 greater than minus C12. You can see that C11 square minus C12 square, that can be written as C11 minus C12, C11 plus C12. And again the product C11 minus C12 is positive, so C11 plus C12 must be greater than 0. But these conditions, but the condition C11 plus C12 coming from question number 8, and also we have this type of result. So we have conditions 1, 2, 3, 4 and 8, and condition number 7, I should say condition number 8 contains the condition number 7. Condition number 7, one part of condition number 7. In condition number 7 we have two things: C11 should be greater than C12, and C11 plus C should be greater than C11 must be greater than minus C12. C11 greater than C12 is coming from here 4, and C11 greater than minus C12 greater coming from here. So condition number 7 lies in 4 and 8. So total we have 1, 2, 3, 4 and 8 conditions for elasticity matrix C of hexagonal continuum. Now this is the exercise for you people. You have to show this. This is for this continuum which we have discussed here, hexagonal continuum. You need to show this. Now we consider isotropic continuum matrix, that elasticity matrix corresponding to isotropic continuum. And we know that in matrix of isotropic continuum we have only two elasticity parameters, which are lambda and mu. We have to find range of values for those parameters, which are called Lamb's parameters, with the help of stability conditions. And we know that stability conditions require the matrix to be positive definite, that the matrix should be positive definite. No, and we also know that for positive definiteness, either determinant of leading decimal minors should be positive, or all the eigenvalues should be positive. Here we will use eigenvalues condition. Now we have suppose that we have two matrices C1 and C2, as we have done in previous for hexagonal continuum, which we have taken two matrices T, C1 and C2. Then we will discuss their positive definiteness. Now this is C1 and this is C2, and these are from the elasticity matrix of isotropic continuum. Now we will find the eigenvalues of these two matrices. I have written directly the eigenvalues. You can see that the eigenvalues of C2 are very simple. They are mu. This is not mu1, this is comma. All the three eigenvalues of C2 are mu, and three eigenvalues of C1 are 2 mu, and this 2 mu, and third one is 3 lambda plus 2 mu. Now you have to find that how these can be obtained with the help of this. Now these are 6 eigenvalues. Now conditions for the positive definiteness of C1 and C2 are, these are the condition when C1 and C2 are positive definite, that when the eigenvalues are positive, then these C1 and C2 will be positive definite. So these are the eigenvalues. So mu is greater than 0. Basically we have 2 mu greater than 0, this is greater than 0, and this is greater than 0. So 2 mu means mu is greater than 0, 3 lambda plus 2 mu is greater than 0, and From here we can write lambda greater than minus 2 mu by 3. Now these are the conditions on parameters mu and lambda. You can also write Poisson ratio with the help of this, range of Poisson ratio with the help of this. Now this is for your exercise. You have to do all these exercise 5.7, 5.8, 5.9, 5.10, 11, 12 and 13, where you can see that different types of expressions are given. You have to compute all those expressions, and then with the help of one expression which will be expression of new Poisson ratio, you will find the range of Poisson ratio. That will be minus 1 to 1 by 2. This is from the book Waves and Rays in Elastic Continua. You must have e-copy of this book. Thank you so much. Allah Hafiz.